This is going to be our second lecture of Module 1. This is going to be Article 110, General Requirements. Our objectives for this lecture, we're going to identify the general safety requirements of the NEC, including equipment working space. We're going to understand general requirements established by Article 110, recognize where to find conductor temperature limitations in the NEC, and we're going to identify ways of identifying disconnects and services. We're going to be bouncing back and forth just a little bit, but essentially what this lecture boils down to is we're going to be talking about different general requirements for equipment and also conductors is a really good way to think about how this lecture is going to be structured. Our definitions, we're looking at nominal, which I would essentially boil down to being normal, suitability, kind of self-explanatory, and a testing laboratory or a NERDL. We're going to be talking a lot about requirements of third-party testing for equipment, primarily equipment. When we do, we're talking about a NERDL. So starting here at Article 110, if you're following along in your NEC for a 2017 edition, this is going to be page 43. So Article 110 covers general requirements for examination and approval, installation, use, and access to and working space for conductors and equipment and enclosures. Essentially, Article 110 is just general safety requirements, is how I tend to view 110 as being safety requirements. And it's divided into 5 separate parts, that being Part 1, general, Part 2, 1,000 volts nominal or less, Part 3, over 1,000 volts nominal, Part 4, tunnel installations over 1,000 volts nominal, and Part 5, manholes and other electrical enclosures intended for personnel entry. An important note here is you can see looking at Parts 2 and 3, Part 2 being 1,000 volts or less, Part 3 being over 1,000 volts. The NEC usually divides sections and articles into those two categories of requirements for 1,000 volts and less and 1,000 volts and over. For the purpose of this course, I'll only be going over requirements for 1,000 volts or less. Now, you may have questions on your exam for 1,000 volts and over, but as far as in the lectures or slideshows, we'll only be discussing 1,000 volts or less. The reason for this being typically the structure and the layout for over 1,000 volts will be the exact same as 1,000 volts or less. It'll just have different, distances or sizes or requirements. But once you learn how to navigate through the 1,000 volts or less, navigating through the over 1,000 volts will be the exact same. That being said, it's very important you pay attention to what part you're in those types of articles, because it's very easy to be looking up a requirement for 1,000 volts or less when you're in the 1,000 volts section. Now, that being said, if we have an article where, as you can see in Part 4, we have tunnel installations, which are only for over 1,000 volts, we will be discussing that since there is not an equivalent 1,000 volts or less section for that. So the first specific requirements we're going to be looking at of Article 110 is we're going to be looking at examination and identification, and this is going to be as it pertains to equipment. So all the following, 110.3 tells us, all the following should be evaluated when judging equipment: the suitability for installation and use conforming to the code, mechanical strength and durability, the wire bending and connection space, the electrical insulation, the heating effects under normal conditions, which is the ambient temperature, and the classification by type, size, voltage, current capacity, and specific use. So kind of looking at each of these individually, they make sense just on a common sense level. So our first point, suitability for installation and use conforming to the code. Obviously, we want to install equipment that is suitable for the application and area we're installing it in, and it has to meet the code, of course. Mechanical strength and durability, we want to make sure that when we're installing equipment, it's going to be suitably durable for the type of environment in terms of, a month from after we install it, it's not just going to fall apart due to wear and tear. Number 3, we want to make sure that where we install it physically, we're actually going to have space for our connections to that piece of equipment in order to energize it. Electrical installation, of course, we want to make sure that touching a piece of equipment isn't going to cause someone to get shocked or electrocuted due to it not being insulated well enough. Heating effects, as we probably all know, when conductors and electrical equipment get too hot beyond what they're rated for, it can cause malfunction or equipment damage. It can cause insulation on conductors to melt or even catch fire. So we want to make sure that the equipment is going to be rated for a high enough temperature for where it's installed. And of course, classification by type, size, voltage, current capacity, and specific use. You know, we need the equipment to match whatever voltage we're going to be supplying it with. We need to make sure it's rated for the type of current that we need to get from it, and so on and so forth. So kind of going off of that as well, looking at installation, use, and listing. Any equipment listed, labeled, or both shall be installed and used in accordance with any instructions included. Essentially what this means is that if something has installation instructions with it, we have to install it per the installations. We can't decide that we like an alternative method better, or that, you know, we think it would be better to install it a better way. We have to follow the instructions exactly as they indicate. Product testing, evaluation, and listing shall be performed by a recognized testing laboratory and used in accordance with the applicable standards. So once again, if we have a piece of equipment that has been inspected by a third-party organization, or as we mentioned earlier, a NERDL, and they specify it can only be used or installed in a certain way in accordance with their testing, we have to follow those standards as well, in addition to any instructions. An example of what this third-party testing is going to look like, if any of you have a piece of electrical equipment next to you, whether it be your laptop charger or a lamp, anything in the USA anyway, that is electrical, likely has one of these stamps on it. This is a UL, or Underwriters Laboratory testing stamp. UL is the largest body in the USA that performs third-party testing. And pretty much any piece of electrical equipment that is used in the U.S. is going to have this stamp from UL on it. So, pressing pause on the equipment idea for a minute, we will be returning to it, but we're going to take a second to talk about conductors now. Some of the same type of standards as we talked about with the equipment. Conductors shall be copper, aluminum, or copper-clad aluminum, unless otherwise noted. Where the material type is not noted, sizes given are for copper. So this first kind of half of this statement we have here, first half of 110.5, tells us that if we're going to use a conductor, it has to be copper, aluminum, or copper-clad, unless the NEC specifically tells us we can use a different type of conductor. The second half is really more intended for when reading the NEC than it is a real-world application. However, there are some instances where this applies. It tells us where the material type is not noted, the sizes given are for copper. In other words, if the NEC tells us a size conductor, whether it be a number 6, a 250 kc mil, whatever it may be, if the NEC does not specify that that is copper, aluminum, or copper-clad aluminum, then we have to assume that that size is meant for copper. Now, in the real world, of course, as we're about to find out in a little bit, we have our equipment, whenever we're terminating a conductor to it, it has to be marked with what type of conductor we can actually use with it. Now, as I mentioned with the number 6 and 250 kc mil, all sizes stated in the NEC are going to be expressed in the American wire gauge or AWG system or in circular mils. And conductors are required to be identified for the environment they're used in. And we have a slide coming up next to talk about that a little more. In other words, if we're going to be installing a conductor in a wet location, it has to be identified as suitable for a wet location. If we're installing a conductor in a corrosive environment, maybe somewhere where they use or make some type of acid, it has to be rated for that as well. So here's kind of a breakdown of how our sizes work. If you're not familiar with this, on the top left-hand side here, we can see in AWG sizes, we start off with a smallest of number 18, and that goes up to a number 1 AWG, which would be largest. So for 18 to number 1, the smaller the number, the bigger the conductor. Then we move on to a 1/0 or a 0 AWG, but that is going to be commonly referred to as 1/0. We move on to a 2/0, 3/0, and 4/0. So with those sizes, the larger the number, the larger the conductor. And on our right here in this larger table, on our left-hand column, AWG/KC mil, starting from the bottom and working our way up, we can see we're getting larger. Then once we hit 4/0, that changes over to 250 kc mil, 300 kc mil, and so on. So once we get past a 4/0 AWG conductor, we're going to be moving on to kc mil after that, which is circular mils. A quick note on this table as well, our very next column, circular mil, if you'll notice, our AWG sizes are also given a circular mil area. And we will need to know that later when doing some conduit and box fill calculations. But that's just a quick note that AWGs can also be represented in circular mils. Now on the bottom left hand here, we can see we have these bold letters T, H, H, W, and N. These are a couple examples of common markings on different types of conductors. And you can see each one of these markings will have a given meaning. So for instance, H, a single H tells us it is heat resistant up to 167 degrees Fahrenheit, which is an equivalent to 60 degrees Celsius. HH tells us it's heat resistant up to 194 degrees Fahrenheit, which would be 75 degrees Celsius. And a W tells us that it is moisture resistant and suitable for damp or wet locations. So an example of a common marking on a conductor would be THHN. So looking at THHN, that tells us that that wire is for T, thermoplastic, a heat-resistant plastic used on many types of wires. The HH is going to tell us it's suitable for up to 194 degrees Fahrenheit or 75 degrees Celsius. And the N will tell us that that is nylon coated to resist damage from oil and gasoline. So that ties back to that suitable for the installation or the area of insulation that we just talked about. Now we're going to be going back to equipment a little bit. Equipment shall be installed in a neat and workmanlike manner. So we actually have a rule in the electrical field per the NEC. We are actually required to install our materials and our equipment neatly and professionally. Actually is a rule we have to follow. Kind of a randomish note here that I wanted to include because it's a very important note. Unused openings not intended for operation, mounting, or as part of the equipment design shall be closed. If using metallic plugs with non-metallic enclosures, plugs shall be recessed 1/4 inch from the outer surface. This note kind of highlights what I was meaning with 110 being about safety. So if we break down these two statements, the first statement about unused openings having to be closed, this is because we don't want people going up to equipment and being able to get their fingers inside of the equipment or hands to where they may touch something inside that's energized and get shocked or electrocuted. And the same concept with this metallic plugs with non-metallic enclosures. This is because typically with a non-metallic enclosure, the enclosure itself will not be grounded or bonded due to it being non-metallic and thus non-conductive. However, if we use a metallic plug with that non-metallic enclosure, that metallic plug is conductive and it could become energized if a uninsulated current carrying conductor made contact with it, and thus if someone were to touch the plug itself in that situation, they could be shocked or electrocuted. So we have to recess that plug from the outer surface of the box or equipment where someone would be likely to touch it in order to kind of prevent them from touching it. And equipment with ventilating openings shall be installed so that they are not blocked. And on our next slide, We'll talk about that a little more because we have some pictures representing those ventilating openings. So this is a common dry type transformer. So on the left side, the left transformer here, we can see at the top all of those openings. Those would be examples of ventilating openings. And on our transformer on the right, we can see those same type of openings on the bottom of the transformer. So if we have any type of equipment that has this type of opening, we can't block or close those off. This is because, as we know and talked about in some of our previous slides, as electrical equipment and conductors get hot, it can cause equipment malfunction or damage. It can cause insulation on conductors to fail, and it could even start a fire. Moving back to a conductor idea, but more specifically the connections and splices for conductors now. As a reminder, as I said, we'd be kind of bouncing back and forth between conductors and equipment. And this is just following the layout the NEC gives us. With all of our lectures in this, we'll just be walking through the article from start to finish. I don't like to bounce back and forth between different pages of the NEC just to make it easier for those of you following along with a book. But because of that, and because of the way the NEC is written, we do have to kind of bounce back and forth between ideas a lot. So we can see that termination splicing devices shall be identified for the type of wire to be used. I mentioned earlier that we would be talking about this, the idea that in field and real world applications, if we have a piece of equipment, it has to be stamped with what kind of wire we can use with it. So if a piece of equipment can accept copper wire, it has to have that copper wire stamp, which will usually be represented with a capital C, capital U. If it can accept aluminum wire, it has to be stamped with a capital A, capital L. And per our earlier note, if it doesn't have any type of stamp, at best, we have to assume that it is only capable of accepting copper wire. Realistically, though, it should be stamped even with just being accepting copper. And part of this rule is because, as we see on our second bullet point here, dissimilar metals such as copper and aluminum shall not intermix unless the device is listed for use. This is to help prevent corrosion and other factors such as that. Obviously, aluminum corrodes differently than copper, so we want to make sure that the type of equipment we're using those aluminum conductors with isn't going to cause that to happen. Another note here, connections using wire binding screws or studs and nuts with upturned lugs are allowed for wire sizes 10 AWG and smaller. Terminals for more than one conductor must be identified as such. So I include this note, even though it's a little bit randomish, because it is very applicable to real world applications. For those of you who have started doing some hands-on training here at BCTC or have done some real world work, the most common place you're going to see this example for the first half of this section number is going to be with common switches and receptacles. Those of you that have worked with those, you know they have the screws on the side that you wrap your wire around and then you tighten down the screw, and that's how you make a connection to it. This would be an example of those wire binding screws or studs that it mentions. A lot of times, due to adjustment factors or voltage drops, you'll be required to use up to a number 8 and sometimes even a number 6 wire for landing receptacles and switches. As we see here, in that situation, you cannot directly attach that number 8 wire to that screw. You'd be required to do something differently in order to make that connection. And then same idea with the real world application. Here, terminals for more than one conductor must be identified as such. I would be willing to wager a lot of you, if you were to open your main service panel in your residency for your neutral and ground bars, you would find that you'd have multiple wires terminated under the same screw. And that is what this statement here is talking about. Each one of those screws individually should be identified as being able to accept more than one conductor. We see a lot of times people like to take maybe a lug intended for a 250 kc mil conductor and put multiple number 6 conductors under that same lug, which would be illegal per 110.14a unless that lug is specifically labeled as being able to accept more than one conductor. And then back to our splicing devices that our 110.14 talked about. Splicing devices shall be listed for use. Connections using solder must be secure before solder is applied, and all splices must be covered in an insulation equal to the conductor. This is a note included because, once again, has some real-world applications. I often see people try to take a ring lug or a fork lug, and they'll just solder a conductor directly to it without making some type of mechanical connection before they do, which would obviously be illegal per 110.14b. This because if the solder weren't in place, the lug and the conductor itself would just fall apart. There's no mechanical means of connection there. And the same idea with the splices point. I've often seen people make the argument that if they splice in some type of non-conductive enclosure, or it happens to be in an area where a person would not be likely to come in contact with it, that they don't need to insulate that splice, and that would also be a violation of 110.14b. Another good note about 110.14b is the way it's worded: all splices must be covered in insulation equal to the conductor. So that is not equal to the voltage applied to the conductor. In other words, if we were using a conductor for maybe a car audio system where it only had 12 volts applied to it, but the conductor were rated for up to 600 volts, and we wanted to repair or make a splice in that conductor, we can't use some type of insulating method, whether it be electrical tape or heat shrink, that's only rated for 12 volts, even though that's all we're applying to it. It would have to be rated for the 600 volts that the conductor itself is rated for. Sticking with that idea about the rating of the conductor, we're going to be talking about conductor temperature ratings. We're going to be talking a lot more about this later in the course, but it's a very important idea, and it comes up in Article 110. So we're going to address it very briefly here. Like I said, we'll be revisiting it later, but this at least gets you looking at it and somewhat familiar with it before then. Conductor temperature ratings must not be larger than the lowest rating of any device in the circuit. A higher rating can be used for adjustment or correction. So what this section 110.14c is talking about is that all electrical equipment has to be listed or rated with what temperature it's allowed to be used with. The most common temperature ratings we see are going to be 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. The reason for this rating is because, as I've mentioned a couple times now, if the equipment gets gets warmer or hotter than it's intended to operate at, it can cause damage to it. So we need to know if a piece of equipment can be used in a 75 degrees Celsius setting, or if it can only handle up to 60 degrees Celsius. The lowest rating of any device in the circuit idea. So for an example of what this is talking about, if we imagine a common situation in a residential application would be we have a breaker in a panel with a conductor connected to it, and that conductor also connects to a receptacle in a wall. Both the breaker, the conductor itself, and the receptacle should all have a listed temperature rating. So the breaker may be rated at 75 degrees Celsius, and the receptacle may be rated at 75 degrees Celsius. However, the conductor may only be rated for 60 degrees Celsius. Since the conductor is rated for 60 degrees Celsius, even though the breaker and the receptacle are both rated at 75 degrees Celsius, we would have to treat the entire circuit as if it were only 60 degrees due to the conductor having that lower rating. We'll talk about that higher rating for adjustment or correction here in just a little bit. Termination provisions are divided into two categories, those being 100 amps or less, 14 AWG through 1 AWG, and over 100 amps and larger than 1 AWG. And we'll be talking about those more in our next slides, starting off with our 100 amps and less. So that 100 amps and less is going to pertain to 60 degrees Celsius conductors. Circuits rated 100 amps or less, 14 AWG through 1 AWG, means we have to use conductors with a rating of 60 degrees Celsius, conductors with a higher rating if the ampacity does not exceed the 60 degrees Celsius rating, and conductors with a higher rating if the equipment is listed and identified for use. And I know this probably sounds just a little bit confusing right now. Our next slide will be talking about the 75 degrees Celsius rated conductors, and then I'll give a better explanation of both 60 and 75 degrees Celsius. So just bear with me through this next slide, and then hopefully you'll get a better understanding of what we're talking about here. So 75 degrees Celsius conductors are going to be for circuits 100 amps and larger than 1 AWG. Going to be conductors rated 75 degrees Celsius. For motors with the design letters B, C, or D, I'll tell you now, and I'll reiterate this in the module when we get to it, which is going to be module 6 when we talk about motors. For the purpose of this course, and also if you go to take a state licensing exam, whether that be a journeyman exam, master's exam, or even an inspector's exam, you will always be assuming that a motor is going to be using 75 degrees Celsius conductors for when you do your calculations for those. Like I said, we'll be going over motors in module 6, so we'll be taking a better look at that then. And conductors with a higher rating, if the ampacity does not exceed the 75 degrees Celsius rating, or the higher rating of the equipment is listed and identified for use. So this is where I said we're going to be getting a better idea of what we've been talking about with these conductors with a higher temperature rating and the 60 degrees Celsius, 75 degrees Celsius, and so on. Now, we're going to be talking about this table in a lot more detail in module, it's either module 3 or module 4. However, as I said, this is a very crucial, very important idea. As a matter of fact, you're not going to be able to successfully make it through module 6 or 7 or your final exam without a base understanding of this table. So this is called table 310.15b16. If you're in a 2020 edition, it's going to be called table 310.16. And this is the table we use to determine the ampacity of different size conductors. So a quick brief of how we use this table. As you can see on our left-hand side in the small red circle, the left side of this table is going to be for copper conductors. The right side of the table in the red circle is going to be for aluminum or copper-clad aluminum conductors. At the top of this table in the large red circle, you can see that for both copper and aluminum conductors, we have a 60 degrees Celsius column, a 75 degrees Celsius column, and a 90 degrees Celsius column. So the way we would use this table as an example, if you look on the very left column, you can see size, AWG, or KC mil. If we go down to a number 10 AWG conductor and then go to the right under the 60 degrees Celsius column, we can see we have a 30. This means that we can put 30 amps of current on a number 10 AWG conductor when using it at 60 degrees Celsius. Now if we go over to the 75 degrees Celsius column, using a number 10 conductor, 10 AWG conductor, we see we can put 35 amps of current on that same conductor. Now this is due to the fact of joule heating. What joule heating works, the more current we have flowing, or amps, we have flowing through a conductor, the warmer that conductor will be, or the hotter it will get. So this temperature rating is actually going to be referring to the insulation on the conductor. So this makes sense if we think about it in the terms of if our insulation is good for up to 75 degrees Celsius, that means we can put more current through that conductor, and thus that conductor is going to get warmer than if it had a lower temperature rating. Because that means if the insulation were only good for 60 degrees Celsius, but we put 35 amps of current on it, that's going to get the conductor too warm for the insulation and could cause damage to it. So now that we've kind of looked at this table, you can go back and rewatch, or I'll make a quick kind of summary here. For applications that are under that 100 amp marking setting, we're going to be using the 60 degrees Celsius column when we take a look at this table. For over 100 amps, we're going to be using 75 degrees Celsius. And as we had noted before, we can use a conductor if we're looking at 100 amps or less. We could use a conductor that has a 75 degrees Celsius insulation on it, but we have to use the ampacity listed in the 60 degrees Celsius column. And I don't want everyone to spend too much time worrying and fussing about this. You won't have questions regarding this table or those temperature ratings on your exam. As I said, this is a little bit complicated of an idea, but it's going to be one of the most important and crucial things you learn in this entire course. And it's going to be very important for finishing the course with a good grade. So I wanted to let you all see it here and get a little bit familiar with it so that when we talk about it later in the course, it's not as new and intimidating. So moving away from conductors now, we're going to be going to talking about equipment again. However, now instead of talking about the equipment itself, we're going to be talking about different types of labels and warnings we have to put on it, starting with arc flash warnings. So in other than dwelling units, equipment such as switchboards, switchgear, panel boards, etc. must be marked to warn persons of potential arc flash hazards. And this label must meet the requirements of 110.21b. So this is kind of just a simple, broad statement. If we're installing a piece of equipment in other than a dwelling, we have to put a label on it that warns there's an arc flash hazard. Now, in addition to this, for service equipment 1200 amps or more, and once again, this is going to be in other than a dwelling unit, we have to put an additional label that contains all the following information. That's going to be the nominal system voltage, the available fault current, the clearing time of the overcurrent protected devices, and the date the label was applied. So the summary of this would be if we're installing equipment in other than a dwelling unit, we have to put an arc flash warning on it. If we're installing service equipment that's 1200 amps or more, we're going to have to put that arc flash warning on it in addition to another label that contains all of this information. These are going to be some examples of those labels. So on the right-hand side here, we have our generic label that was required by 110.21a. On the left-hand side here, we have that label that's required for service equipment 1200 amps and up that was required by 110.21b. In addition to those labels, we also have some required markings and information that some pieces of equipment are required to have. So taking a look at those, equipment must be marked showing the manufacturer, and this includes dwelling units as well. All equipment we install must be marked to show the manufacturer. Other markings such as voltage, current, and other ratings must be applied where specified by the code. In other words, if the code requires us to mark equipment with the voltage, that means we have to mark it with the voltage. Kind of a self-explaining rule there. And talking about reconditioned equipment, specifically, reconditioned equipment must be marked showing the company that performed the conditioning as well as the date performed. It must be identified as reconditioned and the original listing must be removed. So to talk about that just a little bit before we move on to this next note. Recondition, meaning, remanufactured or redone essentially. If we had a piece of equipment that caught fire or something like that, had some type of malfunction, we sent it off to a company to refurbish it, recondition it. We essentially have to treat that as an entirely new piece of equipment, put all new labels and markings on it. We can't just go by the original labeling and marking. And a good note on all this labeling and marking we've been talking about is that all labels required by the code must be permanent and not handwritten. Now we do have one exception to this, which is going to be sections that are variable or subject to change may be handwritten. A good example of where you're going to have this exception is going to be for panel schedules. So in the panel in your home or dwelling, you likely have a schedule in that tells you, breaker number 1 is for the kitchen, breaker number 2 is for the master bedroom, breaker number 3 is for the living room or the den. And the reason that they give this exception to this rule is because you later down the road may move around some of the breakers in that panel or change some of the circuit numbers to where now, circuit number 1 is going to be for the guest bedroom, circuit number 2 will be for the kitchen, and so on and so forth. So we want to be able to easily change those as needed. Sticking with equipment ideas here, we're going to be taking a better look at disconnect equipment and fault current. So disconnects must be marked for its purpose unless its use is self-evident. So what this means is if we just have a random disconnect on a wall somewhere, we can't see what it's going to or what it's doing. Say it's actually a shut-off disconnect for an overhead door, we would have to label that disconnect as overhead door. The exception to this, or an exception in regards to disconnect, is that in other than 1 and 2 family dwellings, that marking we just talked about must also identify the circuit that supplies the disconnect. So in addition to that overhead door labeling, it would also have to identify that the disconnect is fed by circuits 1, 3, and 5, for example. Now we're going to be talking back to disconnect. As I said, we just walked through the NEC in these lectures, so we do have to bounce around a little bit. As you can see here, 110.22a was talking about disconnects, and then 110.24 is talking about service equipment. So the NEC likes to kind of bounce around a little bit, but we are sticking with the theme of marking, because 110.24a tells us that service equipment for other than dwelling units must be marked with the available fault current and the date the calculation was performed. I'm not really going to get into an explanation of fault current. You should learn that, if not now, later in your other courses. But just know in regards to fault current, the marking must show the calculation must be documented for authorized individuals. So that fault current calculation, we have to document that. And when the system is modified and the fault current is affected, the calculation must be verified or redone, and if needed, the labels must be updated. And moving back to disconnects, like we were talking about in 110.22a, if a disconnect is required to be lockable, it must be lockable in the open position. And it's, of course, going to be regarding open as we mean in the electrical field of, if a circuit is open, that means that circuit is de-energized. So we have to be able to lock a disconnect to where the circuit the disconnect supplies is de-energized. And that's going to conclude our second lecture of Module 1. In our next lecture, we're going to be going over working and dedicated space.